Today I am going to explain about garbage collection in Java. Okay, so before garbage collection, you should need to know about the memory structure. I hope many of you know, but those who don't know, I will give you a high level overview. We have heap memory, garbage collection happening in heap memory. In heap memory, we have three types of memory. Again, it's further divided into three: young generation, old generation, and metaspace. Then this young generation again divided into three: Eden space, survivor space S0 and S1. Then this is the high level overview of the heap memory. Now I am going to what are the different types of garbage collection technique. Okay, we have serial garbage collection, parallel garbage collection, concurrent mark soup, G1 GC, ZGC. These are all the different types of garbage collection techniques. And this one CMS, concurrent mark soup, is deprecated and removed from the recent Java versions. Okay, this is nowadays not available. Now we can go to one object lifecycle. Okay, a new object is created. Then it is allocated in the Eden space. Every object, new objects, whenever we are creating a new object, it will allocated in the Eden space. So you know Eden space is part of heap memory, young generation. Okay, so young generation means short-lived objects are living in young generation. Long-living objects are living in old generation. Okay, so here in this young generation Eden space S0 S1 all are short-lived objects. Okay, old generation means long-living objects. Okay, so here whenever we are creating a new object, it will go to the Eden space. Then if Eden is full or not, if it is no means it will remain in the Eden space only. But if the Eden is full, minor GC, minor garbage collection is triggered. Okay, whenever Eden is full, minor garbage collection triggered. So it will check whether our new object is still referenced by someone. If it is not at all referenced, no means it is deallocated, it is getting removed, or it will garbage collected. Okay, if it is still having reference, it will move to survivor space. Our object will move to survivor space. I told you we have two survivor spaces, S0 and S1. So why it is moving? Because garbage collector, before clearing the Eden space, if that particular object is still having reference, means it will move the object to the survivor space and it will clear the Eden space. Okay, so from the survivor space, what will happen? Age counter plus plus, because the age of the object is getting increased, right? So it will check age threshold reached. If the age threshold reached means we will move it into old generation, because age threshold means multiple garbage collection survived. That's how age counter plus plus. Okay, it is if it is survived multiple garbage collections, then it will move to promote to the old generation, because I told you old generation is containing the long living objects. Okay, so now our object is in old generation. Okay, old generation in memory. Initially it was in young generation. It's created in the Eden space, then moved to S0, then S1, then it moved to old generation. Now our object is in old generation. Okay, okay, then if it is here one part is, you can see, if the age threshold not reached, it will still move to S0 S1 like that. It will loop like this. Once this condition is yes, means it will promote to the old generation. Okay, this is the high level about how the garbage collection works. Okay, now I will tell you how the garbage collection process happening. This is one object's life cycle I explained now, right? So garbage collection process, how it is happening. Garbage collection triggered. Okay, we can JVM triggered the garbage collection. So GC type it will check. Is a minor GC or major GC. Major means full GC, full garbage collection. Minor means is a hidden space only like that. Okay, that is a minor. Okay. Minor GC, if it is a minor GC, it will scan the young generation. Hidden S0, S1. Okay, mark living objects. Okay, then it will copy survivor or old generation. Means that living object it will not get garbage collected, it will move to survivor, then from it will move to old generation. Then it will clear the hidden space. Once the moving the copying is done, means hidden space is currently having only objects not having any reference, is ready to be garbage collected. So after the copy it will clear the hidden space. Okay, now this flow, major or full garbage collection, it will scan the entire heap. Okay, entire heap means young, old, everything. Then it will again mark the live objects, means the objects having some reference. Then soup dead objects having no reference, so it will wipe out the dead objects. Then it will memory compact, right? Compact the memory. Then memory is freed up and defragmented. Memory, whatever the objects is there, it will completely free the memory and defragmentation will be done. Fragmentation is happening in the memory, right? If there is some holes or some spaces, everything it will defragment. Okay, this is what garbage collection process. So this much you understand, right? Then I will go to this one by one in the next slide. Okay, so garbage collectors in Java. What is garbage collection? Automatic management reclaims memory, reduces fragmentation. Okay, so this is a low post time. What is the performance goal? Post time should be low, throughput should be high, right? That is our goal. So in terminal, if you are running a Java application, if you want to see the garbage collection logs, you can use these parameters. Okay, if you are using an IDE, you can add it as VM options. It will come. Okay, this is for displaying the garbage collection specific logs. Okay, next, why multiple collectors? Okay, you know that we have different types of garbage collectors. Okay, so Java powers everything from tiny microservices to massive data processing engines, because we have different types of applications, right? Some of them will be plain microservices, some of them will be some complicated logic, data processing algorithms, MapReduce, so many things we have in Java. So same garbage collector may not be sufficient for everything. So depends on our application type, we can choose our garbage collector. Okay, so key decision, how will you choose a garbage collector? First you have to check the latency, then throughput, footprint and heap size. Based on these four, you can choose one garbage collector. Okay, so there is no best GC, the right GC for your specific application constraints. Okay, you have to, there is nothing like the best GC, you have to find a right GC for your specific application. Okay, here this is using another VM options. So you can give like this. If you want to use parallel GC, you can use this option. If you want to use ZGC, you can use this option. This is the way to override the default garbage collector. Okay, if you want to use a specific garbage collector than the default one, you have to give like this. You can configure it in your IDE. If you are running in the production, you can give it along with the VM options. So heap memory structure, young generation we have hidden S0, S1, old generation we have one big space here. So from it's get one from young generation, it is getting promotion to old generation. If a particular object survives multiple GCs, it will get promotion to old generation. So first I will go to serial garbage collector. So stop the world means we using STW, stop the world. Okay, it means it freezes all the application threads to perform garbage collection. Means when a garbage collection is happening, it freezes all the application threads. So this post duration grows linearly with the heap size. So I told you for garbage collection, we need to pause all the application threads. So if the heap size is more, it is directly proportional. The post duration also will be high. So this is about serial garbage collector, okay? Because it is single threaded, only one CPU core it is using, okay? It is very simple, efficient, and has no inter-thread communication overhead. Okay, then small footprint, minimal memory overhead for internal GC structures, ideal for environments which constrain resources. Small applications, it is best for small applications, single core containers or CI/CD engines. Okay, if you want to use serial GC, you have to give like this: serial GC, use serial GC. Okay. So this is a visualization. This is our application threads, the green color. This is the GC thread, the dashed line. Okay, this is the STW or stop the world. This is the post duration. Here in this time, GC will happen, mark and sweep. Then our application threads will resume. Okay, whenever this is happening, all the application threads will be paused. But after this, application threads will resume. That's the idea in serial garbage collector. Parallel garbage collector. So parallel garbage collector, if you want to use, you have to give like this: use parallel GC. Okay, is throughput focused. You will be having high throughput. Okay, designed to maximize the total work done by the application over long periods, sacrificing individual post times. Then multi-threaded, uses multiple threads for both young and old generation collections, utilizing all available CPU cores during the STW process. Okay, and best use cases means ETL, data analysis, so many the high performing things, right? The complicated operations, complicated applications, parallel garbage collector is preferred. So great when total runtime matters more than process. Okay, so parallel GC scales well with more CPU cores, reducing STW time compared to serial. So you can reduce the post time because it scales. If you have more cores in your CPU, it can scale based on the number of CPUs available. So it is parallel. So compared to serial, definitely it will be high performing. It will reducing the STW time or post time. So this is a visualization. Application threads are green color lines. Here you can see multiple dashed lines. This is since it is parallel. In serial there will be only one line, right? Here you can see multiple parallel lines, dashed lines. Okay, GC 1 to 6 here you can see. So in this STW post time, all threads will work on garbage collection. So after that our application will resume. So you will get high throughput, low post time. Next is CMS concurrent mark sweep. This I am not discussing it much because it is already removed from Java. If you want to use, we can use like this in the old version Javas, but in new version you will get an error like this. If you are giving like this, you will get an error. This VM option is not available nowadays. Okay. The issues with this was fragmentation issues. Okay, memory related. That is deprecated and removed. It was a low latency garbage collection technique. This is the visualization. You can see in the memory there is a lot many holes. So this is the fragmentation issue. Okay, it is following like this: application threads, GC threads, concurrent mark it will do, then concurrent sweep it will do. So next is G1 collector. This is Java 9 plus default garbage collector. If you are not giving anything, by default our JVM will use G1 GC or G1 garbage collector. Okay. But if you want explicitly enable, you can do like this: use G1 GC. Okay. So it supports multiple configurations. You can say max garbage collection pause millis. So this much time only it will pause, and you can give initiating heap occupancy percentage. Okay. Start concurrent marking when heap is 45% full. That's what it means. So this kind of configuration it is supporting, and it's a balanced performance. Okay, and it's a region based heap, predictable defaults, the predictable post times, because we can configure the post time. So this behavior is very predictable. So G1 tries hard to meet your post time target. Okay, so this is a default garbage collector nowadays Java using. In Java 9 plus onwards, Java using this. So region based heap and mixed collections. This is the visualization of G1GC. Here the blue color is old region, E means Eden region, green color, yellow color S means S0 or S1, and the one surrounded or having a border like red, it is the collection set or C set. Okay, so G1 adds old regions to C set until predicted post time reaches the target. Okay, G1 splits the heap into fixed size regions. It targets a post time by selecting a collection set of regions to evacuate. So it will mark it with the red. Okay, then it will sweep. This is how G1GC working. So ZGC, this is a low latency GC. It's the scalable low latency GC. Okay, if you want to use ZGC, you have to give like this, use ZGC. Then it's a sub-millisecond process. This is designed for process consistently under 1 millisecond. During garbage collection, there will be a pause, right? So that pause time, if you want to minimize to under 1 millisecond, okay, so we can use this. And pause times do not increase with the heap size. In this, pause time will not increase with the heap size. Okay, so it can handle up to 100 MBs to 16 TB without performance degradation. So massive scalability is there. So generational Java 21 plus separates young and old generations for better throughput enabled by default in Java 21 plus. Okay, so real-time apps, large heaps, strictly low latency. That is the use case for this particular one. So ZGC concurrent relocation, mark the start. Okay, then relocate the start from here. So this in this gap it will do the concurrent marking. Here it will do concurrent relocate. Okay, so this is application in green, ZGC threads in blue, and here colored pointers 64-bit marked 0, marked 1, remapped. This is unused. This is a metadata. This is object address. Here load, barrier and remapping application. Here you can see how it is doing it. This is spaces. If pointer color is bad, barrier traps, relocates objects and updates references. Okay, so this is how the concurrent relocation happening in ZGC. Okay, so this is using when you want massive scalability. Okay, concurrent mark and concurrent relocate will happen. Next is Shenandoah GC. It is low latency collectors. Okay, concurrent evacuation, constant low process, community driven. It's a Red Hat. Okay, GC. Okay, so available in main OpenJDK builds from 8 to 21 plus, and vendors like Amazon Corretto, unlike ZGC, which was Oracle only initially. Okay, post time is independent of heap size. So the advantage is post time is independent of heap size. If your heap is getting increased, still post time do not have any direct dependency with the heap size. If you want to use Shenandoah GC, you can give like this. Okay, so compacts the heap while the application is running. This solves fragmentation versus pause issue. Okay, constant low process. Pause times are typically less than 10 milliseconds and do not increase with the heap size. A 200 GB heap poses the same as a 2 GB heap. Okay, so 2 and 200 will be having same pause time. That is the advantage of Shenandoah GC. So here will give you one quick comparison. Serial parallel G1 ZGC Shenandoah. Okay, G1 is the default. Okay, serial means post time is high, throughput is low, heap size preferred less than 1 GB. Parallel GC is post time is high but throughput is high. Okay, in the same post time, it will give high throughput because of multiple threads. So heap size a medium. Okay, and G1, it is post time is medium, throughput is medium, is suitable for large. This is very balanced because post time is medium, throughput is medium, and suitable for large, and this is the default. Okay, ZGC post time is very low. Okay, throughput is medium. It's huge. If heap size is TB, not even in the GB, then this is preferred ZGC because post time is very low and throughput is medium. The Shenandoah post time is very low, throughput is medium and suitable for large. Okay, and it's owned by Red Hat. Okay, here you can see in this chart, in the x-axis you can see throughput, in the y-axis you can see the responsiveness or post time. Okay, then which GC should you choose? A small application, serial GC, batch processing ETL, parallel GC, general purpose or default, you can use G1 GC, balanced performance. Low latency and large heap, you can use ZGC or Shenandoah. Okay, testing checklist, you can compare the metrics in the production like environment. According to that, you can decide the GC. Okay. Summary and next steps. Okay, so I am concluding here. It's configurable automation. GC is automatic but highly tunable. Choosing the right collector impacts throughput and latency. Okay. G1 is safe default. For most general purpose applications, G1 offers the best balance. Only switch if you have specific needs. Future is low latency. ZGC and Shenandoah enables massive heaps but with sub-millisecond process. Okay, then if you like this video, please like, subscribe and comment. I have done another videos regarding the references in Java, memory areas. If you watch that videos as well, it will be very helpful to understand how it is really works. Okay.